The presenter for the first one is Dawid Dulian. Dawid is a 30-year-old IT engineering student at the Silesian University of Technology in Gliwice, and hopes that his dive into debug-friendly C++ templates will make them the powerful and broadly used tool they were intended to be from the very beginning. Hence the title of this presentation. Please help me welcome Dawid. Dawid, the floor is yours.
Hello, is this working? Okay. Hello and welcome everyone to my lightning talk. Thanks for coming. And the topic is how to enjoy the templates, how to use them with joy, and how to especially debug them, because that's the biggest issue with them. So first, I would like to ask you three very brief questions regarding the templates themselves. I would ask you to raise your hand if you know what templates are, how to generally use them, and how to implement one. Please raise your hand. Okay, grand majority. Fantastic. Out of those people, I would like to ask a second brief question. Who does actually use templates regularly or semi-regularly? Okay, so 80% around, great. The third question, out of those people, who thinks that the templates in their basic form are like comparably enjoyable, like reasonably enjoyable, like comparable to other programming challenges? Barely anyone. Okay, thank you very much. I also don't think that they are enjoyable in any sense because of the reasons I will present next. But those people that do enjoy them, great. They're great. They provide great functionality. But not many people, as we can see, actually share this enthusiasm. And this talk will help you write code that will make your templates enjoyable for other users. And people who don't enjoy templates, welcome. That's why you're here. And I hope you learn something that will make it change. So first of all, a little reminder about templates. This is a code that would really use some templates because it is a function duplicated 3 times. It's not universal, and templates change that because we can just, instead of our type, like int double character that we define, we can just say that it's our type name that we insert everywhere where there is we need to use our type. And we define it, we specialize it when we use it, like lines 9, 10, 11. It's a great feature. And compiler does the rest of the work for us, and it is great. Templates are fantastic, they're great. They have a great idea of how to improve coders' life. But why are they so hated among the programming community? So here's the reason. That's why they are hated. Many people I heard that are familiar, unfortunately, with this monstrosity, because that's a casual error that results from using templates. That's just the template programmer's life. And this one specifically was a user from Stack Overflow, unfortunate one, that forgot to implement a comparison operation in their class that they used in one single function when the comparison operation was used exactly once. And this is the error. So yeah, this is rough. That's why they are hated. And they are so much hated that even there were talks how to get rid of those errors. And takeaway was to avoid using them like fire and just don't use templates at all and use other stuff, just forget about it. And for me, that is ridiculous because they provide such a great functionality that is gate-kept behind the error messages that are frankly unreadable. Maybe readable, but like 50% time, 50% like reading into errors is actually like overstatement because yeah, template errors are just very rough. So what do we do with those errors? Because they are not user friendly, right? We can't see what's happening, and we should do something about it. So how about if this error, this one singular block of error that could easily be 7, 8, 9 screens long, if we change it to something like this, much better. We are told where the error is, line 22, and we are told what actually is wrong with our code. So function template comparing function is missing, something went wrong. So that would be much better. So what's actually missing from our templates functionality? First thing is clear errors, obviously. And second one, explanation. What kind of data types work with templates? What kind of functionality those types must provide? Because what's better than easily resolving errors? Easily avoiding making errors in the first place, right? So that's exactly why concepts come in. And this error messages, those little ones, were exactly what the concept error messages, those were the concept error messages. So they are short, simple, and they tell us exactly where to look for the error. And they are made before templates are even pasted into action. And second one, explanation on kind of data types work with templates. Concepts are made so that they are themselves an accessible interface that tell us what exactly needs to be present in our data types in order for the template functions and classes also to work properly. So that is great. So concepts are basically requirements for our data types and for their properties. So we can, for example, require type to implement operations like comparison operator, have specific properties like member functions or variables, or maybe be specific type, and work properly in specified context. On that in a second. And that's the functionality. What do they do? But how do we use them? It's also very simple. We include concepts library, then we create a concept and we name it, and we substitute the type name keyword for our concept's name. So it's very easy. So maybe we will give an example. Right now it's just regular function that sorts a container, be it a vector, list, maybe deck, or anything else. So we have those template function, and we sort container inside. That's it. So how do we do it with templates? So that's how. First, we define, we add the include concepts, line 4 already done. Then we define our concepts body. And then on line 11, we substitute type name for our sortable, because that is what our type should be, sortable. And how do we actually define a concept? A template type name T, just as all the templates go, then concept keyword, our concept's name, and equals. And then we have all the requirements. For example, with the keyword requires, there is we put the operation that must not throw any errors inside those inside the parentheses, and that's it. That's our first concept implemented. There are also concepts that are already made for us that we can check into instead of type name keywords, and that's all great. For example, more mathematical, integral, floating point, totally ordered. We can use it just like that. But also for more programming related issues, we have those next. For example, sortable, move constructible, copyable, destructible, etc. And honestly, the first one, SD sortable, we just implemented. It's basically the same functionality. And these are just a couple. I picked a couple that are nice to showcase. But there are two that we will use once more in the presentation: SD convertible to and same as. They are quite different, but they can also be used as all the others. So That is actually all that you need to know to use the concepts. So that's this part of the presentation. And now I prepared some more examples when we showcase how to use them actually. So first is requiring operators methods. Let's jump straight to the example in a second, because it's basically we require operators to be present and functions to function properly, to be present and to not throw any errors. And here's an example. We have a function template simulate growth, and we do some things with our parameter that we pass onto this function template. It doesn't matter, but here we have it. So what do we do? No, first, we include concepts library. Then we substitute type name keyword for this concept name. Let's call it, for example, growable, because simulate growth, growable. And we create a function body. Concepts body. So here it is. Then we define requirements. So our requirements is line 16. There's default constructor with no parameters. Line 18, comparison between two objects. Line 19, .upgrade method. And then SDCout defined and object.changes must be also present. So we have those requirements, and we put it inside. So that's basically all that we need to do. We just, there's all. I don't think I need to explain further. But there's one thing more. The comparison needs to be between two operators, not operators, between two objects. So we just add another one. And instead of t more than t, which is also OK, we just switch it to t less than q or more than q, because it's just a bit safer. And then next topic, checking functions return times. Basically, what if our member function or variable or any other return type needs to be a specific one or convertible to other specific one? We use same as or convertible to inside of the concepts to define what types the return types need to be, how they need to function. For example, we'll go to example shortly. But these concepts are a bit different because they have those angular brackets, right? So they're actually not that different from the others, because there are two ways to create concepts, is just the notation. So let's use the SD integral, but it works with any other type. This one above is just used as the concept, and this one below is used in our custom mate concept that we are specifically making, right? And in our own example, we use those angular brackets because we need to define what type needs to be, what type it needs to be. There's also the third syntax, but we won't go into it at all. But just for the presentation is complete, I needed to include it. So let's get rid of it. And how do we join concepts together? Just simple logic, because it's just very intuitive, and we can just decide that our number needs to be either integral or a floating point, because that's a common use case, right? Okay, so this example, I don't have much time left, but this example we are presented with just lines 4 to 8 are important here. For example, we have the type that represents a pair, and the first argument needs to be convertible to unsigned character, and second convertible to double, because that's our requirements. We decided that it's working the best way, this way. Okay, inheritance and polymorphism is rather not common, but interesting, because with inheritance and polymorphism, templates provide their own way to implement polymorphism, right? Because we decide what types our functions need to be specified to work with. right? And it's quite universal. So that's the first thing, and using concepts with classes that also use templates, it's just adding another layer of abstractions, and errors can get messy. So using concepts is like actually very beneficial. But also important other thing is that, let's go here. The types that are in libraries, the other external libraries that we use, we should be able to use those algorithms, for example, functions, their classes, with our own types. And this orange table let's assume it's the external library, and a great programmer provides us with a concept, shape type, that decides what kind of functionality does a type from his own function needs to have in order to function. So we can we users of this library can create our own functions and classes that satisfy those requirements, and those requirements are great, and we can use them, and we should be able to use them always. And last place, I don't have time at all, so just a little mention. STL containers, algorithms like vector lists, deck, and algorithm library. It's very common to use those types of containers inside our own functions and use their functionality. For example, here's a great example that we insert. We have function templates where we insert to the container the same number of elements, but they are multiples of pi number. And for example, it's a great concept that we defined. It needs to be pushbackable and needs to have size that is convertible to size t. It's very, very nice. And I don't have time for this example, but the takeaway here is that it is a good practice to split concepts into one singular functionality that can be used many times. So, for example, we split our parsable sortable container that prints elements into two concepts: one parsable sortable container, and second one to have printable elements. And that's actually all that I had prepared for this presentation. So to sum up, concepts are great to work with templates. They provide clear errors and clear interface what needs to be done in order for the types to function properly. And it's just a fantastic way to improve your code, whether you are writing it or using it, or maybe both, probably both. So I would like to thank you all for joining, and also I would like to join my team and our teacher and research guide, Grzegorz Wojciech Kwiatkowski from Silesian University of Technology, because he decided that it would be a good idea for us to be here, be present, and share those knowledge. So thank you all for joining, and that would be all. Thanks.